Welcome. In this video I'm going to show you how you can perform a modified likelihood ratio test of goodness of fit using Microsoft Excel. In this video I'll explain how to perform the test, not so much if you should be using this test. There are alternatives for this test, but in this video I'll just go over how you can perform the test. I have a separate library, an add-in that I make myself, which actually has a function for this, but I'll discuss that in a separate video. In this video I'll show you how you can do it without any additional libraries. First of all, we need some data. I've taken some data from the General Social Survey and stored it in column A. The first step is to determine the number of categories, which in this case was 5. I then listed all the possible options and counted how often each occurred using a count if. By the way, I'm using a semicolon and your system might be using a comma depending on your system settings as a parameter separator. And counting, of course, the specific category. Pulling that down gives me all of the results and the total as well. Now, I'll be using as expected count simply the total sample size divided by the number of categories, but perhaps you have some expected counts for each category up front, so then you can just enter them here. Now we calculate the natural logarithm of the proportion of expected over observed. So we take the expected values and divide that by the observed counts, and then take the natural logarithm for that and multiply all of that with the expected. So if we look here, unless it's 0 of course, but if it's 0 then we simply keep it at 0, and otherwise we do the expected count times the natural logarithm of the expected count divided by the observed count. I can simply copy paste this down again, and then I have this result as well. Now the test statistic is actually the sum of all of these, so that's what's being done here, and then multiplied by 2, so that's the chi-square test statistic. The degrees of freedom is fairly straightforward. You take the number of categories minus 1, in this case 5 minus 1 would be 4, and then you can use the chi-square right-tail distribution function from Excel by feeding it the chi-square value and the degrees of freedom. If you want, you can also do a correction, the Yates continuity correction for example, which says to subtract a half if the observed count is greater than the expected, and add a half if it's less than. If it's equal, just keep it the same. So we had the original observed counts, the original expected counts, and now what I'm simply doing is doing 3 if statements, one for each of these, or actually 2, and the last one false would then be the last one. So if it's greater than the expected, then do minus a half, otherwise if it's less than do plus a half, and in all other cases simply put then the observed count. Alright, then we do the same formula as earlier on, but now we're using these adjusted observed counts, sum them all up and multiply it by 2. You can also do a Pearson correction, which is actually a factor that applies towards the chi-square value, which is simply the sample size minus 1 over n. So I had the sample size in F15 minus 1 over F15, and then multiply the chi-square value with this factor. There's also a Williams correction, which for this case would be the number of categories plus 1 over the sample size times 6 plus 1. So that's being calculated here, and this one you actually divide the original chi-square value by this, so we get this result as a new chi-square value, and then you can use the chi-square distribution again to find the corresponding p-value. In all of this, in this case it's so low, it's actually 4.5 divided by 10 to the power of 273, which is below the usual threshold of 0.05. So we would say it's a significant result, and therefore in the population most likely the counts are not going to be equally distributed. Okay, I hope this video was helpful, and thank you for watching.